Hello, welcome to lesson 11.2 on trigonometric functions of general angles. This is our second lesson on trigonometry out of a 5 lesson span. This lesson is going to be getting into the actual kind of trigonometric functions is what we call them. A trigonometric function will describe a ratio of side lengths in a triangle. There are 3 of these that we want to remember. That we want to make sure we have memorized. So there is sine, cosine, and tangent. These 3 things describe 3 different kinds of comparisons. So if you're comparing the opposite side to the hypotenuse, you're talking about the sine. If you're comparing the adjacent side to the hypotenuse, you're talking about the cosine. And if you're comparing the opposite to the adjacent, you're talking about the tangent. So these are always done from some angle's point of view. So the opposite of this angle would be this side, whereas if we were saying the opposite of the angle up here on the top, it would be down here. Okay, so that the hypotenuse will be a fixed location because that will always be the longest side of a right triangle. But the other 2 sides, the opposite and the adjacent, are dependent on what angle you're talking about. So the way that we'd say this, we'd say that the sine of this angle is the opposite divided by the hypotenuse. The sine of this angle basically tells you how what percentage of the hypotenuse is this opposite side. Is it like 50% as big? Is it 20% as big? Is it 90% as big? That is generally what the sine is telling you. It's comparing this side to the hypotenuse, and the number you're always going to get will be less than 1 because we're never going to get a opposite side that's larger than our hypotenuse. So our fraction's always going to be less than 1 here. Same thing will be true about the cosine. You'll be comparing the adjacent side to the hypotenuse with cosine. So that'll be telling you, kind of what percentage of the hypotenuse is the adjacent side. Is it 90%, 80%, 60%, 50%, all the way down to 0%. It will not go above 1. However, tangent is a little different. Tangent can go above 1. Now, if you kind of notice, opposite over adjacent is exactly the same thing as your slope. So, right, your rise over your run. So as you would kind of understand from that, slopes can have values greater than 1. They can be, up to infinity if we want. So we can have a slope of 1, 2, 3, 4, 5, 6, 7. We can increase the slope of this triangle's face. We can kind of bring this corner up, and that would cause our tangent to increase. So tangent is the one that we're kind of like the most familiar with already. We've just called it slope in the past. It is important to keep in mind, though, for me to compare this to slope does sort of require us to have that angle in the bottom left. So for example, if you looked at this one in the top left, if we do opposite over adjacent, the value that we're going to get will not be rise over run. It'll be run over rise, right? So tangent is not always identical to what we think of as slope. It kind of just is contextual to the way that we have this image set up. But it's a good thing to kind of point out and notice. So that's what these 3 trigonometry functions are. They're ways of describing ratios of side lengths in a triangle. Now, originally, these things were just found by hand. So if somebody wanted to know what the sine of 30 degrees was, for example, they would take a protractor, they would measure a 30-degree angle, something that would be roughly like that. And then they would literally just measure the opposite side and the hypotenuse. Okay, so they would do that, and then they would find what that fraction equals. And they would say that the sine of 30 degrees, that ratio, is the opposite side over the hypotenuse. They would measure it with like a ruler. Then they would take that value and they would put it into a table. And what that would generate is just a large reference guide. Let's try to find one in here that would tell you what to expect for any given angle. Okay, given some angle, what would we expect the ratio of the side lengths to be? Okay, so sorry, it's a little blurry, so I'll just read it out. Hopefully you can see it on your own computer. So this would be like a table of values. This is on Excel, obviously. This is not like a pen and paper one. But back before we had computers, this is how we would have been doing this. So there'd be people measuring different size angles, 1 degree, 2 degree, 3 degree, 4 degree, 5 degree. And you would see that, for example, with a 1 degree angle. So some really, really, really skinny angle here. I think they are doing cosine, yeah, COS, cosine. So they would say that the cosine of an angle is equal to the adjacent over the hypotenuse, right? The adjacent side down here, here's my angle, the hypotenuse. Now, the adjacent side here is just barely less than the hypotenuse in length. So this fraction should end up being, roughly, based off the way I drew it, I'm kind of intending it to be roughly like 0.99. Okay, about 99% as big as the hypotenuse. And if we look at that table of values, that's what we see, 0.999 something, something, something. As the angle increases, that value decreases. So by the time that we get out to like a 45-degree angle, and we're looking at something more like this, well, then my adjacent side over my hypotenuse, that ratio is not quite as close as it was before. In this case, the cosine of this angle, this like 45-degree angle, is going to be roughly 0.7 by this point. So this is about 70% as big as that piece. Okay, so trigonometry started out as a way to connect our understanding of like the expectations of how there's a connection between the angles and the side lengths of a triangle. So if I get a 45-degree angle, it does not matter how big that triangle is. So I can have a large triangle, I can have a smaller one, I can have a smaller one. As long as each of these all have that 45-degree angle in that corner, then um, whatever like this hypotenuse is right here, this small hypotenuse, this one will be 0.7 of that. Okay, whatever this larger, medium-sized hypotenuse is, the adjacent side down here will be 0.7 of that value. Okay, so that ratio does not depend on the size of the triangle. It only depends on the angle that that triangle has included in it. Okay, so that's kind of the connections that were made by doing trigonometry originally. Now, let's kind of hop into the book real quick. So, trigonometry is the study of relationships among the angles and sides of triangles. A trigonometric ratio compares the lengths of two sides of a right triangle. A trigonometric function relates the angles of a triangle to the lengths of its side. Okay, so let's try to break that down. A trigonometric ratio is what is meant by like what does sine mean? What does this word mean? Well, it is a trigonometric ratio. It's the ratio of the opposite side divided by the hypotenuse. Okay, that is the trigonometric ratio. The trigonometric function is slightly different. The idea of the function is that if you apply this little function to some angle, so if we say the sine of, like I just used in my example, sine of 30 degrees, I'm going to get out some answer, okay, 0.7. This is a function because there's an input, that's like our x variable, and there is some output, which we could think of as like our y variable. Okay, so they are very closely related. When we say trigonometric ratio, we're just talking about the definition of what each of these words mean. So for example, sine meaning opposite over hypotenuse, cosine equals adjacent over hypotenuse, tangent is opposite over adjacent. These are the trigonometric ratios. The functions are when we actually apply these in an equation. When we apply that function to some angle and we get some answer. Okay, where we have an input of an angle and we have an output of a ratio. That's when we are applying it as a function, as something that's actually doing work on some information. So a trigonometric function relates the angles of a triangle to the lengths of its sides. If this is, by the way, theta, if you've never seen that before, this is a Greek letter. So I will be saying theta when we see this guy right here. If theta is the measure of an acute angle of a right triangle, then the trigonometric functions involving the opposite side, which we label op, the adjacent side, adjacent, and the hypotenuse, hype, are defined as follows. Okay, so we have our sine, our cosine, and our tangent. It's very important to have this mnemonic phrase memorized, SOHCAHTOA. Now, there are three other trigonometric functions, trigonometric ratios that we can talk about, and it's cosecant, secant, and cotangent. And if you notice, let's start with tangent. Tangent and cotangent are just flipped over. So the cotangent is just comparing the adjacent to the opposite. So this one would give you a value that was like maybe, the opposite is 70% as big as the adjacent. Whereas this one would say the adjacent is, oh, sorry, that would be a bad example. Let's talk about cosine, cosecant. Sorry, I'm getting mixed up here. Let's pause for a moment. Okay, so we have our three main functions, and then we have our three kind of inverse functions. So you just want to kind of pay attention to which ones get flipped. So opposite over hypotenuse, over here we have hypotenuse over opposite. Adjacent over hypotenuse, hypotenuse over adjacent. Opposite over adjacent, adjacent over opposite. Now these are just saying the same thing, but they're saying the ratio from the other one's point of view. So if I look at opposite over hypotenuse, that was where, for example, I would say that like the sine of 30 degrees equals about 0.7. Okay, that's telling me that the ratio of my opposite to my hypotenuse is 0.7, which means that this guy is about 70% as big as the hypotenuse. Now, if we were to use cosecant, which is the inverse of sine, the value we would get is just, 1 divided by that. Okay, that gives us 1.42. Okay, so 1.4. So that just means that our hypotenuse is 1.4 times larger than our opposite side. Okay, so it's the same information, it's just depending on which thing you want to talk about. Do you want to talk about how big the opposite is compared to the hypotenuse? Well, it's about 70% as big. Or do you want to say how big is the hypotenuse compared to the opposite side? Well, it's about 1.4 times larger than the opposite side. It's the same information, just said from two different points of view. Now, with sine, cosine, and tangent, it kind of turned out that there was a fairly simple mnemonic device that sounds okay when you put them together. So sine is opposite over hypotenuse, that's your SO. Your cosine is adjacent over hypotenuse, and your tangent is opposite over adjacent. Now, unfortunately, there's not quite a mnemonic device that I know of that comes to mind over here. Like, we're not going to say cosecant is hypotenuse over opposite. Secant is hypotenuse over adjacent. Cotangent is adjacent over opposite. Doesn't sound very good, does it? So, not very easy to remember. So these ones can be tricky to remember. I'm not going to ask that you guys memorize them. I was kind of looking into, what are their uses to kind of talk about that today. And I kind of mostly just came up with people arguing about whether or not they're very useful. There were some statements made about like the inverse ones, like cosecant, can be useful in polar coordinates. So polar coordinates are like a graph that's not based around straight lines in both direction, but are based on concentric rings. So like if you see, a submarine radar, that is polar coordinates. So evidently cosecant can do some interesting things when applied to like different coordinate systems, but we will not be getting into that anytime soon. So I'm not going to focus on it too much. I also saw other people just saying that like in other countries, they just don't use these things. So, up to you how much you want to spend your time thinking about these inverse ones. But really the way where we want to focus is over here, sine, cosine, and tangent. Though you will see an occasional homework problem that will use these ones. But you can go back into the book and reference that if you need to. The key concept shows how to define the 6 trigonometric functions by using ratios of the sides of a triangle. Alternately, once sine and cosine are defined in this way, the remaining trigonometric functions can be defined in terms of sine and or cosine. For example, since sine of theta is opposite over hypotenuse, 1 over sine of theta is hypotenuse over opposite, which is the same ratio used to define cosecant. Okay, so they're basically saying once you've created definitions for these two are just inverted versions of those. Additionally, you can get to tangent, I believe, by kind of combining these two. So let me think. If you wanted opposite over adjacent, I think you just multiply these two, right? If I multiplied these two fractions, I'd cancel out, or would I? No, I'd need to flip this one. So if I took secant and I multiplied it by sine, hypotenuse is on the bottom of one fraction, it's on the top of the other, we'd get opposite over adjacent. So they're saying that like once you define these two, you can define these two by just flipping it over, and you can define tangent even by multiplying sine by secant. Okay, just kind of a thing to point out and think about, but not going to be totally essential to what we're working on. Okay, so we will move on to example number 1 in our next video.